Hello everyone, this video is a short tutorial about embedded bare metal bootloader. At the beginning I should say that everything is done under Linux, so if you are not very familiar with it, you could observe my another video about STM32 development under Linux. I'll add a link with video the same as a link to described software. Actually, this demo is done also using a STM32 board, but the idea can be used on another platform. For STM32 Cortex-M3, just configuration for another MCU, the hull should be replaced. At the start, a few words about bootloader, what is that and what to do with that. That's very easy to protect commercial embedded software from copying. Just set a flash lock bit on your MCU and that's everything. But there is an open question during the maintaining stage of your software. And the main question is how to deliver the software, caused by implementation new features or bug fixing. In that case, bootloader is used. Bootloader is a small application which able to start your main application and of course update your main application in some way. Actually, at customer side exists two problems. First, it's software hardware equipment to make flash procedure. And the second is that you should show your application to customer. Even if you set lock bit before, it's not very good idea because seems very strange. So the proposed software solves both of this issue. The first one is relative to equipment. In this sample, used the internal MCU USB port in CDC mode, which is a virtual serial port. In that case, customer just need a USB cable and standard serial port terminal, for example, Minicom. The next one regarding to enclosure your application, your hex file, is that you can deliver it encrypted hex file. So you just encrypt it and provide to customer encrypted file. And customers actually know nothing about the content of this file. The bootloader worries about decrypt this file and flash this file into your MCU. On MCU there is lock bit, so there is no any problem. Customers still have no access to your flash memory. So let's start with our application. I already have downloaded this application. Here it is. First, there is folder. I will show another. It's your encryption key. It's AES key. It's binary file, but you should hide this file because that's your encryption. So let's start with regeneration of this key. Some keys are prepared beforehand and committed into repo, but if you will use real application, you definitely should update this key. So this key is updated. For updating is using very simple script. It just random data, put it into this file. After that you can compile bootloader. Just make procedure and let's flash our board. That's cleaning. That's flashing bootloader. Everything is done. After that, that's very important. You should do power cycle with this board. So you configure a bootloader in our case is selected by these jumpers on the board. It's boot 1, which is not used. So it's bootloader and start power cycle. You see the green light is on. That means that it's established a connection with your personal computer. Let's check it. In that case, you should have new serial port in your computer. Here it is. Let's open this port. We can type help to see available command. The most important command for beginning is information. It shows the information about memory layout, so it's occupied by bootloader, and after that it's your application section. The main difference and the one difference between usual STM32 application and bootloader application, it's that application addresses which should be put it in linker script, because now your memory not start with default STM reset address but from another address, and of course the amount of this memory is a little bit smaller. Let's now leave bootloader and start with compiling test application and all procedure, how it works. So that's our test application. Test application is very simple and stupid. It's just blinking this LED. That's everything what it's do. Okay, you have compiled your application, but now you should encrypt this application. So we have some custom software for encryption, which do AES encryption. We compile it and run. Actually, everything is done, so you can see your encrypted file. It's in folder test application. So it's your original file, and that one is encrypted. We can compare this file. As you can see, they are different. The differences are highlighted. Addresses, all addresses are the same, but the content, data content, is encrypted and maybe very different from original application. So this one, it's your real code, and this contains some kind of shit, so it can be executed on MCU. It's nothing. Actually, for encryption is used the AES encryption, which is some kind of standard, and it's symmetric encryption. So if you need to decrypt, you can just encrypt again your encrypted files. Let's check it. Okay, now see at the result. So encrypted. Let's compare this file again. The first one and the last one. As you can see, they are identical. So content now is decrypted. Okay, and now we can download our software, encrypted software. So we issue the command program. Now we should send our encrypted hex file. And choose an encrypted file. It's sending. Actually done. And let's check the status of our program. The program is okay. So let's check our application. So we go to our board, select application, and reset the port. As you can see, it's blinking. So application is touched. Finally, we can check our read protection. Okay, and try to read. As you can see, reading error. Let's try to do init reset. Nothing, just reset it and read again. As you can see, the error. Actually, we know that it's locked, so we try to unlock. Now it's unlocked by suggestion to do power cycle, but let's start to read without power cycle. Now we should do it. OK, and try it again. Yes, now it's successful. And let's check this file. As you can see, everything is already clean, and if you realize it, it's already not operable. No replication, no bootloader. Nothing. Green light is off. So it's a proof that protection is working well. Actually, that's all. Thanks for attention.